To finish up with another complete example of brittle failure using the brittle Coulomb Moore and modified Moore. But before we continue, maybe we should take a look at the selection of failure criteria, when to use which criteria. So you'll notice that we have a ductile region and a brittle region. And so what they're saying here is we want to take the fracture strain. I believe that's what they're meaning by a fracture strain, right? So if the fracture strain is greater than 0.05, we consider that ductile. Or if it's less than 0.05, we use brittle. That's what they're saying that the thing is from. So this is the strain at fracture. And there's not many places that you're going to find that, I think. But I did look it up and looked for it, and in my notes I say if you go to table A22, you're able to find some data for that. Right, so these are results of some tests, tensile tests on materials, and you will actually find a true fracture strain right there. So true fracture strain is what they're calling that, and notice that they're all above that 0.05, right? So yeah, 0.05. So all of these would be considered ductile materials based on that criteria there. Did they say, oh, they also said in 23. Okay, here's a lot more of these. Let's see, this is a weird one that they're almost calling this, it looks very similar here, right? This symbol, but it's actually this guy, the true fracture strain. And once again, we don't see anything that you would be considered a brittle material. And we can continue down while this really goes down a lot further. Nothing below 0.05, right? So none of those. Now, I don't know if I kept looking here, would I find? No, they don't give us this for the gray cast iron, which is considered brittle, right? That is considered one of the things. So it's interesting to me that we don't have any real examples in Shigley where I see any of these. I'm still looking for there's just there's statistical things for some materials. Yeah. So I wish they had some more examples where we would be able to use this figure, but I guess in general that this is one that we could if we're considered the thing brittle, this is another piece of information that we could use to try to decide whether you're going to be and then so coming down in the ductile side, we ask if the tension yield strength and the compression yield strength are the same. This is generally true, yes. We didn't really even look over at this ductile Coulomb Moore idea, but it's very similar to what we just did in the previous two examples in this section. It's just we use ductile Coulomb Moore, right? If they're not equal to each other, if there's some difference between tension and compression, whether tension's bigger or compression's bigger, we would use this failure theory right here. But this is the one that we generally have done for ductile. And then they have this question, do you want to be conservative or not? Yes, you want to be conservative, use maximum shear stress theory. No, you don't want to be conservative, you want to be instead more closer to what you believe is going to be the correct answer. Go with distortion energy theory, aka von Mises. He's the way to go. On the other side over here, if it's brittle, right, so the fracture strain is less than this right here, 0.05, then you go to the brittle side, and if you want to be conservative, we use brittle Coulomb Moore, and this is the one that we're going to go with most often. Well, pretty much all I care about, brittle Coulomb Moore. No, you don't want to be conservative, you want to be closer to reality, go with modified Moore. All right. So let's go to an example, longish example, where I do a bunch of stuff. Right? So It's probably repetitive, maybe a little repetitive. I have it here as try it, but then I decided to combine this topic with the introduction to fracture mechanics, and then make the next class more of a review class. So I don't think I'll have you trying this in class, because it would take up the entire period basically to solve this problem. But instead, we will go ahead. I'll work it here. So we don't have any bending involved. We can see that right away. All we have is axial and torsion, and we have a groove going on here. So if you were going to take a look at what this thing would look like here, we have like a kind of a groove that looks like something along those lines right there. All right. So that's what the cross section, or the side view, I should say, of this thing would look like. And what they're saying here is that it's 3/64 inches deep, which would be that distance right there, but the radius is 9/64. Okay, so this distance right here. All right, so let's go to this distance right here. If this main guy is 2 inches, right? So right here is 2 inches diameter, and that radius right there, that's something we're going to need, is 9/64. We'll look that up here in a second. And this depth right here is 3/64. So that means that this diameter right here, which we'll probably call low d, this is big D right there. This is going to be big D. Well, I'll just go right and use the numbers. It's going to be 2 minus 2 times 3/64. And if we go with a value, this is going to be 1.9. Slow down. 1.906 inches. And if you wanted to get, this is going to be the radius, and it's going to be equal to 0.1406 inches. So when we go to look up the stress concentration, we get 2 divided by 1. I did it again. I don't know what's up with me in writing that down. 1.906, which is 1.049. I did it on purpose. R over D is going to be 0.1406 divided by 1.906, and we get 0.07378. So let's look those up. We'll do that right away. Get it out of the way. We know we have to do it, so we might as well get it out of the way. So we find those stress concentrations. We're going to use axial and torsion. We don't have any bending this time. So what did we say? We had 1.049. Look, 105. Ha ha ha! Did it on purpose. And they got 0.7378. 0.7378. So that's for close to 0.075, right? So close to this and close to this. So that looks, and by the way, that's 2.2, 2.4, 2.6. Okay, so 2.3 is halfway in. So it looks like 2.3 and change. Oh, man, what happened here? Nope, I went up too high. That was 1.15. I need to go to this guy right here. Yep, oops, yep. I was looking at the wrong curve. Occupational hazard, right? So this is 1.8, that's 2.2, so this must be 2. And so this is just below 2. I said that it was 1.98. That's pretty nitpicky. You could go with 2. 1.98, so I'll write that down. That the KT is approximately, and this is from A15 13, and this is 1.98. And then this one's going to be from A15, which one? 1515. All right, so it's torsion. We have the same dealio here. Here's our 1.05. Here is the close to 0.075 right in there, and it's just above 1.4. I said that was 1.42. Right, and you can argue about this if you wanted to. So this is from 15. We see that KTS is approximately 1.42. And you're going to use the little d as the little d is the basis for the nominal stress. So the area is pi over 4 and 1.906 squared, or 2.83853 inches squared. And J is going to be pi over 32, 1.09, wow, I keep doing that. Something stuck in my head that somehow, and let's raise to the fourth. There we go. And so that is 1.296 inches fourthed. So the nominal stress in this, just F over A, so 25,000 divided by 2.853, and so we end up getting 8, I'm going to go KSI, 8.762 KSI. And let's go to the nominal, TR over J. So we get the torque is 35,000. And the R is now going to be 1.906 divided by 2 divided by J, 1.296. So we get the nominal is going to be 25.74 KSI. So the maximum is just going to be the KT times the nominal, or 1.98 times our 8.762. We end up with 17.35 KSI. And then the tau max, this is not the abs max, remind you. It's just the maximum due to the stress concentration, and that's going to be 1.42. And our writing it down wrong, 25.74, and so we get 36.55 KSI. And now we need to get the principal stresses in order to use this, right? So we're going to write down on a stress element. We have stress that way, stress, shear stress that way. And so we have our 17.35 KSI, and we have our 36.55 KSI. And doing a little more circle action coming up onto here. I think I'm going to be down here. All right, so here's our C. Oops. And here's going to be sigma A. Here's sigma B. And C is simply going to be 17.35 divided by 2. So that comes out to 8.675. And our R is going to be right here. right? So that's just the C in this case, 8.675 squared, and then the 36.55 squared. And we end up with 37.57 KSI. So our sigma A, C plus R, turns out to be 46.24 KSI. And my sigma B, C minus R, so now it should be a negative value, right? So we get negative 28.89 KSI. And so one thing we want to know, one thing we want to check here is our ratio of B to A, sigma B over sigma A, is for the modified Moore. Remember why we're doing that. Remember we have this sloping line with a slope of 1 right here front is pure torsion. Above this, for modified Moore, we just take the ratio of the larger principal stress, the sigma A, and the ultimate tensile strength, right? Actually, the other ratio the other way around. The ultimate tensile strength divided by sigma A is the safety factor. That's what they say right here, or actually right there. But then, like, if the value of B over A is greater than 1, then we use that, because that means that it's down here in this range. So that's something to check, and we can see that we have 28.89 divided by, and this is absolute value, 46.24, and what we'll find from that, I didn't bother doing this right here, but we have 28.89 and 46.24. We get 0.6248, which is less than 1. So therefore, when we have a safety factor for our modified Moore, is simply going to be the ultimate strength divided by sigma A. We don't even use sigma B for anything. So that's simply going to be, oh, we didn't look it up. All right, so I need to look it up. This is for ASTM 60. So the ultimate strength and tension for this is 62.5 KSI. That comes from like table A24, I think. And in compression, it's a large 187.5 KSI. So if the safety factor is the 62.5 divided by our 46.24, 62.5 and 46.24, and divide, and you get a 1.35, right? But now for the brittle Coulomb Moore, we're going to use this equation right here, because we're in this quadrant, so that's correct. But now we're using this, what's the dashed line right there is what we're really kind of referencing. And that's the brittle Coulomb Moore. And so we have the sigma A divided by the tension, right, minus sigma B divided by the compression ultimate strength. Remember that minus is because that's minus right there, right? So don't subtract them, actually subtract them. And so this is the 187.5 minus, but here's the minus 28.89. And, oh, I messed up. That should be the 62.5. And here should be the 187.5. Remember, this is apples to apples, right? So these are tension, these are compression. That's why we're taking the ratio of them. So the brittle Coulomb Moore safety factor ends up being 1.12. That's interesting, right? It says way smaller than this. Let's take a look where that lands, though. if we can. We probably have to really get in here. I'm not going to do the ratios of these right here. But we want to take our two principal stresses, which you'll recall are going to be 46. Let's call it look like more like 45 and 30, right? So because we have very small increments right here. So it looks to me like we're kind of at 1, 2, 3, 4, 5. We're kind of by tens, right? So in the positive, we're going to have 46, which is pretty darn close to that 50 right there, right? So this is 45. Yeah, let's just call it right there, 45, right in there, right? And then this other is 30 right there, so that's probably like right in there. So we get pretty darn close. Right in there. So you can see how close it got to the brittle Coulomb Moore, whereas right here is where the modified Moore is going to be. So you get kind of a sense of where this point is fitting right in here. Now I got an interesting thing. I said that compared to the distortion energy theory, I don't think that's true. That's an interesting. If you were to take the distortion energy theory instead, it shouldn't be that much smaller. I don't know. But anyway, I'm not going to even check on it. It's a good problem to maybe check with the to check with the FEA, right? But we wanted to use we want to find von Mises for this. So maybe for von Mises, let's just do a really quick check. I'm just curious now that this is going to be equal to. I'm going to use the maximum, so 17.35 squared plus 3 times 36.55 squared. Taking the square root of that. What does that end up equaling? 17.35 squared and 36.55 squared, but then times 3, add them together, take the square root. I get that we get a 65.64. Are these KSIs? Yes, KSI. Compare that to the tensile strength, right? The tensile strength is 62.5, so sure enough, interesting, that we're outside of those bounds. I guess that makes sense to some extent, right? If we were to maybe make this thing, this right here would be where the maximum shear stress theory would go right there. You can see we're outside the maximum shear stress theory, and then the distortion energy theory is just round in the corner right there, right? So yeah, we're still outside the bounds right there. So this fails according to for the on the ductile side, if that in fact had the limit. I'm using the ultimate strength, but yeah, interesting. So there you go. That was a long example, but worked out. An extra example, 23 minutes of your life. You're not getting back. We're going to do fracture mechanics next, so introduction to fracture mechanics.